Professor Belfrost's science class is back.
Hi, welcome back to this channel. And today we'll again discuss another concepts related to science. So here's the science tutorial for you today. Are you ready? Let's continue playing this video. Good. So yeah, let identify first. Okay, so the next thing that we'll learn in this chapter is about reaction yields. Okay, so the relative amounts of reactants and products. Let me check. Okay, you have seen it. The relative amount of reactants and products represented in the balanced chemical equations are often referred to as stoichiometric amounts. Okay, and all the exercises of the preceding module, I mean the preceding session, involves stoichiometric amount of reactants. Okay, for example, when we calculate the amount of product generated for a given amount of reactant, it was assumed that any other reactants required were available in stoichiometric amounts. Okay, and in this module, that more realistic situations are considered, and in which reactors are not present in the stoichiometric amounts. Now, point 11.8, which is the limiting reactant. Okay, consider we follow this way to make a grilled cheese sandwich. So one slice of cheese plus two slices of bread makes one sandwich. Make one sandwich. So stoichiometric amounts of sandwich ingredients for this recipe are bread and cheese slices in a 2:1 ratio. And if we have 28 slices of bread and 11 slices of cheese, how much you think we can, the sandwich that we can make? At most, maximum number of sandwich we can make. Okay, we see 2:1. Okay, if we have 11, it means that we need to have 22 slices of bread, right? So yeah, this is the limiting agent actually. Okay, so we can only prepare 11 sandwiches. Okay, and there are 6 slices of bread will not be used. Okay, in this scenario that the number of sandwiches prepared has been limited by the number of cheese slices and the bread slices have been provided in excess. And also this can be applied regarding to a chemical process. So for example, the reaction of hydrogen with chlorine yields hydrogen chloride. So hydrogen plus chloride makes 2 hydrochloric acid. And the balance equation shows the hydrogen and chlorine reacts in a 1:1 stoichiometric ratio. And if these reactants are provided in any other amounts, that one of the reactants will nearly always be entirely consumed, and thus limiting the amount of product that may be generated. So the substance is the limiting reactant, and the other substance is the excess reactant. Okay. For example, imagine combining 3 moles of hydrogen, 3, by 2 moles of chlorine. Yeah. Okay. Certainly, this is the limiting reactants, right? Okay. So 1.5:1. Okay. And yeah, this is not the correct ratio because the ratio here is 1:1. So yeah, the hydrogen is present in excess and chlorine is the limiting reactant. An alternative approach to identify the limiting reactant involves comparing the amount of product expected for the complete reaction for each reactant. Each reactant amount is used to separately calculate the amount of product that would be formed per the reaction stoichiometry, and reactant yield and the last amount of product is the limiting reactant. For example, from the previous one, okay, I mean this one H2 plus Cl2, okay, hydrogen gas plus chlorine gas produce 2 hydrochloric. Okay, so 3 more of hydrogen times 2:1. Okay, it produces 6 more of hydrochloric. 2 moles of chlorine times 2:1. It is 4 more of hydrochloric. and the chlorine will be completely consumed once 4 moles of hydrochloric have been produced. Since enough hydrogen was provided to yield 6 moles of hydrochloric, there will be unreacted hydrogen remains when the reaction is complete. You see, and the limiting reactant is the chlorine, and hydrogen is the excess reactant. Now let's see the example. Identify the limiting reactant. So silicon nitride is a very hard, high temperature resistant ceramic used as a component of turbine blades in jet engines, and it is prepared according to the following equation: three silicon solid plus two nitrogen gas. It becomes silicon nitride. So which is the limiting reactant here when 2 gram of silicon and 1.5 gram of nitrogen gas reacts? Okay, so first we need to compute a provided molar amount of reactant, then compare this amount. Okay, so 2 gram times 1 by 28 point, this is a molar mass of silicon. It gives us 0.0712 mole silicon. And this one, N2, is 1.5 times 1 by 28.02. This is 0.0535. So the silicon by nitrogen molar ratio is this. Okay, well actually this is 3 by 2, right? 3 by 2. So it actually needs to be 1.5 by 1. Okay, but this is 1.33 by 1. Okay, so silicon is provided in less the stoichiometric amount, and so this is the limiting reactant. Okay, alternatively, can compute amount of product expected for complete reaction of each of the provided reactants. So you see here and here, and you see the lesser one, this one, right? So this is the limiting reactor. I want you to check the learning by trying to solve this one. Now point 11b, percent yield. Okay, so the amount of product that may be produced by a reaction under specified condition as calculated by the stoichiometry of an appropriate balanced chemical equation is called the theoretical yield of the reaction. Okay, and the amount of product obtained in the practice is called actual yield, and often less than theoretical yield for a number of reasons. Okay, some reactions are inherently inefficient, being accompanied by side reactions that generate other products, and others are by nature incomplete, and some products are difficult to collect without some loss, and so less than perfect recovery will reduce actual yields. And the extent to which the reaction's theoretical yield is achieved is commonly expressed as percent yield. So this is the percent yield. Percent yield equals actual yield by theoretical yield times 100%. So actual and theoretical yields may be expressed as masses or molar amounts. And as long as both yields are expressed using the same units, then this unit will cancel when percent yield is calculated. Okay, so this is 1.274 times 1 by 159.62 times 1 by 1. Okay, this is to find the mole of the copper sulfate. Okay, so we need to find mole of copper sulfate by this way, and then we need to convert it to the mole of copper by stoichiometric factor like this, and then we need to find the mass by multiplying it by the molar. Okay, the inverse of the molar mass, and we get this. Okay, so percent yield is lesser, right? Because we only get 0.392, and actually we are expected to get this. So this is only 77.3%, the percent yield. Okay. Now next point, quantitative chemical analysis. Yeah, so I want to read this paragraph by yourself. And the ones that described in the paragraph is actually what called quantitative analysis, which is the determination of the amount or concentration of a substance in a sample. And in the case of analysis of vinegar, that the concentration of the solid acetic acid was determined from the amount of reactant that combined with the solid present in known volume of the solution. And other types of chemical analysis, that the amount of substance present in a sample is determined by measuring the amount of product that results. Let's see some quantitative analysis. First one is titration. Okay, so yeah, titration analysis typically involves the use of burette. What is burette? Which one? This is burette. Okay, this is burette. The one that is used by this guy, this equipment. I mean, this tool. Yeah, this measuring tool. This is called burette. Okay, to make an incremental addition of a solution containing a known concentration of substance, which is the titrant, to a sample solution containing the substance whose concentration is to measure, which is the analyte. And the titrant and analyte undergo chemical reaction of known stoichiometry, and so measuring the volume of titrant solution required for complete reaction with the analyte at the equivalence point of the titration allows calculation of the analyte concentrations. And the equivalence part of the titration may be detected visually if a distinct change in the appearance of the sample solution accompanies the completion of the reaction. Okay, in the case of the classic vinegar analysis, more commonly we apply special dyes, which is the indicator that we add to the sample solution to impart a change in color at all very near the equivalence point of the titration. And regardless of the approach taken to detect titration equivalence point, then the volume of titration actually measured is called the end point. Here's an example. Let's see. So the end point in the titration is for 50 milliliter sample of aqueous hydrochloric acid that was treated by addition of 35.23 milliliters of 0.25 or more of sodium hydroxide titrant, and the titration reaction is this. So what is the molarity of the hydrochloric acid? So let's follow this way. So volume of natrium hydroxide, moles of natrium hydroxide. Yeah, from volume, and we know the molar concentration, I can find the moles of the natrium hydroxide image like this. Okay, and then we convert it with the stoichiometric reaction, which is HCl and this one, yeah. So one by one, the stoichiometric reaction is one by one. So one by one. This is the one that we expect, 0.25 molar times 1 more shell 1 more. Yeah, this is the stoichiometric factor. This is the conversion. Okay, so this is, and then we can find the molarity by dividing mole by the volume, and it gives us this. So you can find it directly by using this. To check your understanding, I want you to solve this. The next one, gravimetric analysis. So yeah, a gravimetric analysis is one in which the sample is subjected to some treatments that cause a change in the physical state of the analyte that permits its separation from other components of the sample. Okay, so gravimetric methods were the first technique used for quantitative chemical analysis, and they remain important tools in the modern chemistry laboratory. Okay, the elemental composition of hydrocarbons and related compounds may be determined via a gravimetric method called a combustion analysis. And a combustion analysis, a waste sample of the compound is heated to a high temperature under a stream of oxygen gas. Okay, and a complete combustion of hydrocarbons, for example, will yield carbon dioxide and water as the only product, and the gases combustion products are swept through separate pre-weigh collection devices containing compound that selectively absorb each product. It's like this. Okay, let's find out this concept by analyzing this problem. Okay, gravimetric analysis. So a 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of barium nitrate, resulting in the precipitation of 0.6168 gram of barium sulfate. So what is the concentration of mass percent of magnesium sulfate in the mixture? So we actually process with like this, and the mass of magnesium sulfate that will yield the provided precipitate mass is like this. Okay, so this is conversion to find the mole of the barium sulfate, and then this is convection factor, and then we find the mole of magnesium sulfate, the gram of magnesium sulfate by uh, multiplying it with the molar mass, and it gives us this. And we can find the percent mass, right, by the mass of magnesium sulfate by the mass of sample, which is 0.4550 times 100%. This is 69.91% by mass. To check understanding, I want you to proceed with this uh, question. Now, combustion analysis. Polyethylene is hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. And the combustion analysis of a 0.0126 grams of polyethylene yields 0.0394 gram of carbon dioxide and 0.00161 gram of water. So what is the empirical formula of polyethylene? So like this, see? So yeah, first calculate the amount of carbon and hydrogen in the sample using a provided mass of carbon dioxide and water. Then we can follow this approach. Okay, easy. And here we process it. Okay, yeah, and this is the result. Okay, I think that's all. That's enough. Chapter is finished. The next discussion must be revision. I mean the discussion of problem of this chapter. I want to share a quote for you before I end this video. You must do the things you think you cannot do. Yourself. I mean that you need to challenge yourself to do the thing out of your comfortable zone. That's the end of the video for today. Thanks for watching. Thanks for following so far. And here's what you need to do. Please subscribe, give a thumbs up, comment, and share this video to your friend. And also, don't forget to check our website at https://science-exploits.unaux.com, and I'll be back on every Tuesday, so keep watching and be thoughtful. Goodbye, see you on the next episode.